Good day everyone, this is Helena Nazarova from Skolkovo Institute of Science and Technology. I'm glad to present our work HyperPalm, DNN-based hand gesture recognition interface for intelligent communication with quadruped robot in 3D space. First, I would like to discuss why in this work was used a four-legged robot and not a wheeled one. Currently, wheeled robots are very popular among all mobile robots, but they lose to four-legged robots in the passage of a complex surface, as shown in the table, and this is critical. However, absolutely any robot, even the most reliable one, can get stuck. In such cases, the operator can take the remote control. The main problem that while joysticks and keyboards are convenient for the wheeled robot, the quadruped robot in 3D space can move along all linear coordinates and earlier angles, requiring at least 12 inputs for independent control. Several researchers try to solve a problem similar to ours. They have various strengths and weaknesses, which we will try to analyze and solve. First work, Swarm Paint, controls a swarm of drones using a gesture interface. This work has high accuracy in classification, doesn't use any additional devices for control, but is based only on changing linear coordinates. Further, excellent work is devoted to determine the 6D position of the object. This is a strong model that works in real time with RGB images. However, such network will not work well with an object that can change its shape, such as a human hand. The singled out this week based on the experiment that we conducted. It will be in a few slides. The third work, OpenDog, was developed together with NVIDIA. This is one of the first work that introduced communication between a human and a four-legged robot using gestures. The operator communicates directly with the robot, but he doesn't have any visual feedback. In our team research, the aim is to achieve intuitive communication between quadruped robot and operator without additional devices and without limitation of the 12 dov of robot motion. The novelty is hand gesture interface based on DNN with high accuracy of hand recognition in 3D space to real-time control position and orientation of quadruped robot developed by our team. To achieve it, I developed a DNN-based hand gesture model with 6D hand pose estimation and the control system. By 6D in this work means 3 linear and 3 angular degrees of freedom in 3-dimensional space. This video shows a HyperPalm system that works according to this control system. The operator can control the linear coordinates and earlier angles separately or together by switching the control mode. The operator shows a gesture called 1 to achieve linear control mode. Next, the operator should show the open gesture to initiate the calculation of the relative hand movements in 3D space. Finally, the operator demonstrates the close gesture to disable 3D hand control immediately. The earlier angles control of the robot is activated by performing the 2 gesture, combined linear and angular by 3 gesture. The system overview represented on this slide. The developed HyperPalm system includes 2 Intel RealSense cameras, NVIDIA Jetson Nano, and operator PC. The first camera is located on the robot and captures the RGB image of its front view. This image is used for operator to have understanding of the remotely located robot localization in the environment. The second camera captures the RGBD image of the operator's hand. The operator's PC processes the input data through the hand gesture module. This module sends control data to the onboard computer NVIDIA Jetson Nano using ROS. The output can be recognized gesture or 6D hand position. Next, the onboard computer processes the input data from the gesture module in the control system module and sends movement commands to the robot itself. For static gesture recognition, we selected to use a fully connected network with 4 layers: input layer, 2 hidden layers, and output layer. The input data is XY coordinates of 21 hand landmarks which were extracted using high-fidelity hand-tracking solution MediaPipe hands. As input data also was used 20 normalized vectors length between landmarks. This parameter encourages the model to be invariant to the position and orientation of the hand. Thus, in total, the model takes 62 parameters as input. Moreover, between layers, the network has ReLU nonlinear function and batch normalization. It has resulted in accuracy of 96.5% when performing validation on a test set. If the probability of the gesture is less than 85%, the algorithm takes the predicted gesture as none. Determining the position of three linear coordinates of the hand, implemented by calculating 3D center of mass and analyzes its linear movement in space. The information obtained about Z coordinates, its depth, for each landmark from a pre-calibrated depth image in meters. The algorithm for calculating hand Euler angles consists of three parts. First, extracting X, Y, and Z coordinates of 21 hand landmarks as for determining the position of three linear coordinates. In addition, was implemented an algorithm to generate a point cloud of the hand, using key nearest neighbor approach. You can see the intermediate stage of building a point cloud on the GIF and the figure. The next step is an approximation of the point cloud to a plane by least squares approach. And first, defining the three angles of a plane. Two approaches for determining the 6D position of the hand in space were tested. First, YOLO-based CNN model for 6D pose object prediction using project vertices of the object's 3D bounding box, and PNP algorithm. For this, we collected our own dataset with RGBD images, binary masks, and 3D model of the hand. Second approach is our method based on the MediaPipe, depth maps, and building point cloud. In addition, to validate these two approaches, 6 participants were invited. Each participant disposed in front of the collaborative UR3 robot with a statically directed hand towards the camera, which is located on the robot. The robot moved along a pre-programmed trajectory along linear and angular axes. To compare two 6D pose estimation approaches, the standard RMSD over all participants who took part in the experiment was used. The linear RMSD result for YOLO-based approach is 23.6 mm. For proposed method is 11.7 mm. The angular RMSD result for YOLO-based approach is 3.6 degrees. For our proposed method is 2.6 degrees. After the experiment, each participant was asked to control the robot using gesture interface, and after asked to complete the questionnaire based on NASA TLX, extended by one additional question. In user experience summary, intuitiveness level of gesture interface appeared to be high. However, some participants had to work hard to reach their level of performance. Several users felt high temporal pressure due to pace of the tasks. As a result, the developed system allowed to classify 5 static gestures with high accuracy, accurately predict 6D position of the hand in 3D space, and NASA TLX showed that participants found the gesture control interface as intuitive. In the future, we will provide the additional experiment with a scenario close to the real industrial environment. In this experiment, participants will be asked to navigate robot along a particular trajectory using several existing control interfaces and the developed HyperPalm interface. Moreover, in the future, we will adapt the gesture recognition for various lightning levels and visual noises. Thank you for your attention. Now I am ready to answer your questions.